Hello friends, welcome back, and today we are going to solve Harvard's problem of the week 85 named Tower of Cylinders. Consider the infinitely tall system of identical massive cylinders and massless planks as shown below. The moment of inertia of cylinders are I equals to mr square by 2. There are two cylinders at each level. The number of levels is infinite. The cylinders do not slip with respect to the planks, but the bottom plank is free to slide on the table. If you pull on the bottom plank so that it accelerates horizontally with acceleration A, what is the horizontal acceleration of the bottom row of cylinders? Let's say the bottommost plank is being pulled with the force F, and which results in its acceleration A. So let's try to draw a free body diagram of the bottommost plank and the two bottommost cylinders named as L and R. Now let us say FL be the friction force between the cylinder L and the bottommost plank, and let FR be the friction force between the cylinder R and the bottommost plank. Similarly, FL dash and FLR be the friction force between the cylinder and the next plank. Let's try to find out what should be the relation between FL and FR. Well, we know that acceleration of the bottommost point of both the cylinder has to be same because both of them are in contact with one plank. Similarly, accelerations of these topmost points should also be same because both of them are in direct contact with one plank, and the plank is moving with one acceleration. And this is only possible when acceleration of center of mass of both the cylinders as well as the angular acceleration of both the cylinders is same. And again, it is only possible when FL is equals to FR and FL dash is equals to FR dash. So from now on, we will not consider two separate friction. Instead, I can directly say that FL plus FR is equals to capital F. Why? Because the planks are massless, so forces has to be balanced, and we know that FL is equals to FR, so I can say both of them are F, so 2F is equals to capital F, so I can say the friction is equals to F by 2. So we are going to use term F instead of L and R as notation from here onwards. So now we have removed the subscripts L and R, and now let's try to find out what should be the relationship between F and F dash. For now, let us assume that F dash is related to F as equals to K times F equals to K times F. Now let's try to write the force balance equation for any of these cylinder, and that is going to be force balance, or just force, we can write force equation, and that is going to be F minus Kf. This is equals to mass into acceleration of center of mass, we denote it by ACM. Similarly, let's try to write an equation of moment. And that would be like moment of friction force F plus moment of friction force Kf, and this is equals to moment of inertia, and let us say alpha is the angular acceleration of this cylinder. Now let us remove the two bottommost cylinders from our imagination and also the bottommost plank from our imagination, and let us consider our system as the remaining tower of cylinders. You see, now we have the second bottommost plank here, and to know the forces acting on the second bottommost plank, we are going to use Newton's third law, and by Newton's third law, the forces on this plank is going to be equal and opposite to this force and this force, and hence I can say the forces on the second bottommost plank is going to be 2k small f, where small f stands for friction, and which is equals to k into applied force F. Remember, friction force we have already found out is equals to applied force divided by 2. Now, do you see some similarity here? Well, this is also a stack of cylinder running from bottom to infinity. This is also a stack of cylinder running from bottom to infinity. Geometrically, both of them are same. The difference is the force on this system applied on the bottommost plank is F, while for this system it's K times F. So it would be logical to say that if the acceleration of this plank is A, acceleration of this plank is going to be K times A. And from this we can conclude that the acceleration of bottom point of the cylinder is going to be A, while for the top point of the cylinder is going to be Ka. And from this we can find out acceleration of center of mass, ACM, which we had in our force equation, and that would be A plus Ka divided by 2. Similarly, we can also find out angular acceleration for the cylinder, and angular acceleration can be written as A minus Ka divided by 2 times R. Now let's substitute acceleration of center of mass and angular acceleration in our force and moment equation, and the result is going to be F into 1 minus K is equals to M into A plus Ka divided by 2, and from moment equation we can say F R into 1 plus K is equals to half mr square, and alpha are now known in terms of A, K and radius. Now this equation has got two variables. First is friction, second is K, factor K. I can divide these two equations to find out K, and I can see, so by dividing these two equations I get 1 minus K upon 1 plus K is equals to 1 plus K upon 1 minus K divided by 2, so 2 comes in the numerator. Solving this for K gives us K is equals to minus root 2 minus 1 upon root 2 plus 1. Well, the question asks what is the acceleration of center of mass of the bottommost cylinder, and we know that it is A plus K by 2. So acceleration of center of mass is equals to A by 2, 1 plus K. Let's substitute K here, and that would give us A by 2, 1 plus K is equal to root 2 minus 1 upon root 2 plus 1, which is, and this results in A by 2, 2 upon root 2 plus 1. After rationalization it becomes A into root 2 minus 1. This should be the acceleration of center of mass. Thank you very much.